So in this video, we're going to introduce kind of what is this idea of a reduction in a little bit more formal terms, and then kind of describe how it applies to this idea of topological sort. So a reduction in kind of its most abstract form is a problem-solving strategy that involves using some algorithm for a different problem to solve the problem at hand. So we're going to talk about these reductions in terms of these very abstract terms of you're trying to solve this problem P that you don't know how to solve quite yet, and a reduction is changing the input for problem P into some input that you could use in an old problem you already know how to solve, call it problem Q, run the algorithm to solve that problem that we already know, and then take that output and then change it into some output to solve the original problem. So reduction is about changing the inputs and outputs rather than making a modification to the algorithm. We're trying to make our new problem compatible with some known problem, Q. And we use this terminology that P reduces to Q to describe that we're able to do this conversion. So a reduction actually kind of has three parts to it. The first is converting an input for problem P into an input for problem Q, then running that predefined algorithm Q, then taking the output of that algorithm and converting it back into your original problem space. So before talking about any computer science examples, let's try to use an analogy to get a little bit of intuition about this process of a reduction. So suppose I want to get a note to my friend in Chicago, but I don't really know how to solve that problem on my own. Like I'm not about to go walk all the way to Chicago to go deliver a note to my friend. So it'd be nice if I can take this novel problem, this one that no one has experienced before, because this is my first time trying to write a note to my friend, and let's try to reduce it to a problem that we already know how to solve. For example, trying to put in the mail and using USPS to deliver the mail for us. So what the idea here in a reduction is to take this novel problem, this new problem of sending a note from Seattle to Chicago, and reducing it to, in this case, the more general problem of just mailing a letter. So the reduction would operate in a couple steps. Start with my note from Seattle, and the first step of the reduction is to put it in an envelope. That envelope can act as the input to the mail a letter algorithm, which implementation might be use USPS, which I kind of showed here as kind of animating through. Oh, it doesn't show the animation again. That's weird. Okay, whatever, PowerPoint. But we saw a little USPS car driving by, assuming the USPS still exists since the time of this recording of the video and when you watch it. I assume it will still be there at least temporarily. But we mailed the letter to Chicago, and then our friend has to take that envelope and then open it to get our letter back. So this reduction is kind of a three-step process. Putting the letter in an envelope, calling this mail a letter algorithm using USPS, and then the third step is taking the letter out of the envelope. This process describes a more general notion of reduction, changing our novel problem, getting a letter from Seattle to Chicago, into a problem we already know how to solve, just mailing a letter. So now let's try to use this idea in topological sort. Here's the idea. Instead of changing the BFS algorithm, let's change our graph. So the change we're going to make is we're going to add a phantom node. This phantom node is going to be a modification to our original graph such that it makes sense for BFS. The idea is add this phantom node at the beginning, and it has an out edge to every vertex that has a 0 in degree originally, kind of those roots of the graph, the ones that don't have any incoming edges in our dependencies. The idea is add this phantom node that kind of points to all these starting points. What we're doing here is we're reducing this topological sort to BFS. We're trying to change the graph input so that BFS can work on it. So now we can just run the BFS algorithm, starting with this ghost node and just running BFS kind of as it was written on the pseudocode a couple slides ago, kind of outputting all of the nodes in the order it visits them level by level. And this kind of respects all of these dependencies. However, a very important note is that this output is not good for our original problem. Notice it has the ghost in the output. It's the first node. That ghost node is the first thing in the output. That was not in our original problem. You didn't have a ghost class you had to take before you can graduate. This kind of output from BFS is on this modified problem. The third step of the reduction is to take this output and turn it back into an output that's acceptable for the original input that you were given. And so for this example, we simply just have to take out the ghost node. So we just remove the ghost node and return the rest of the ordering. And that is a proper topological ordering for this graph. So the key idea here was in all of these steps, we modified the input and the output to BFS. So we used BFS as a subroutine to help us solve this problem. But instead of trying to change BFS, we changed the graph. We changed the input and output. That's the idea of a reduction. In some sense, reductions aren't new. You've used reductions in your entire programming career, solving a problem in terms of a problem you already know how to solve. But now we're giving you a terminology, some vocabulary to describe what is this process of changing inputs and outputs in terms of these other problems. Now, this problem-solving strategy of reduction is so useful when it comes to coming up with algorithms to solve problems you haven't seen before. I'll quickly mention that this idea of a reduction shows up quite a bit in computer science. Particularly, it shows up in the world of CS theory, so theoretical computer science, where we try to make statements about problems that we don't even know how to solve yet. So if you can show that one problem P reduces to another problem Q, you could make statements about these problems even if you don't have an algorithm to solve either of them. This idea of a reduction serves as a very fundamental building block for how problems relate to each other. And lets us make statements about runtimes and solvability of problems that we don't even know how to solve quite yet, which is just a really powerful tool. So now that I've talked about this general idea of what a reduction is and applied to this topo sort, I want you to practice this. So now that we've achieved the sweet victory in figuring out topo sort, let's practice this idea of reductions. So think back to Wednesday, when we solved the unweighted shortest path problems, which I abbreviate as USP for this slide so it doesn't take up a bunch of space. We solved that using something like BFS. So my question here is this a reduction? Did we reduce USP to BFS? Or did we do the opposite, reduce BFS to USP? Or is this not a reduction at all? Take a second and think through this. What do you think that we did with BFS? This question will only be multiple choice, but I want you to make sure you have a reasoning behind your answer. Take a second on your own. Okay, so now that you had some time to think about that, let's go ahead and tackle this. So I would argue that this is not a reduction. Why? Well, in order to solve this unweighted shortest paths problem, we took BFS and modified it to create this the shortest path tree and this dis2 map that required a change in the algorithm. So reductions, importantly, aren't changes in the algorithm, but rather changes in the input and output so that we can use a pre-existing algorithm. So there is no reduction relationship between unweighted shortest paths and BFS, even though the algorithm we came up with for unweighted shortest paths was heavily inspired by BFS. Inspiration is not the same as a reduction. In our next video, we're going to talk about some more examples of reductions so we can get more practice with this idea.